In 10.4, we're going to apply the two most basic and fundamental concepts that we learned in calculus concerning slope and area to the topic of polar curves. In this lesson, we're going to take all those graphs that we looked at in 10.3 and apply those, again, calculus ideas of slope and area to these polar functions. Okay, so the first calculus concept we're going to address concerning polar functions are going to be tangent lines. But there's two distinct categories of these tangent lines, and you're going to really need to see the difference so that you don't get the two confused. The first type are going to be tangent lines at the pole. To find tangent lines at the pole, or the origin, we're going to set r equal to 0 and solve for theta. That's going to help us find the angles of the tangent lines the curve follows as it approaches the origin, or again, the pole. These are not the tangent lines like we've been used to finding, like the dy dx version of tangent lines. These tangent lines are the lines that the curve follows as it approaches the origin, and we'll do a visual of that so you can see what that looks like. The other type of tangent line and its slope is kind of the one that we're used to, but this is a much more complicated formula concerning polar functions. If you want to find dy dx, your slope machine, like we've seen way back since chapter 2, to find the slope at a point on a polar function, we're going to need to use this formula right here. And it's rather involved, and there's really no maybe trick to memorizing it, other than you maybe finding some pattern to help you remember this particular formula. So again, there are these two different types of tangent lines we can find concerning polar functions. The first type is going to help us once we start trying to find areas inside polar functions. This tangent line at the poles is going to be very important for us to try to, again, find areas inside polar functions. This slope, on the other hand, is just our regular slope like we've seen again since chapter 2, where we're trying to find the slope of a tangent line on a polar function. So to illustrate this idea for both of these tangent line types, we're going to take a look at this polar function, cosine 3 theta. I want to find the tangents at the pole and use that to help sketch this rose curve. So the first thing we can realize as a review from 10.3 is that if our n is equal to 3, the number in front of theta is odd, we're going to have equally spaced petals of that number. So in this case, we'll have 3 equally spaced petals. In addition to that, the number in front of our trig function cosine here, which is a 1, is going to tell us how long each of those petals are. So the length of each petal, in this case, is 1. The other thing we need to keep in mind is, and again, it's going to be very important so we don't trace over the graph that might already exist, is that we need to realize when that number n is odd, our petals are generated as theta goes from 0 to pi. As soon as we pass pi, we'll be tracing over the graph that already exists, and of course, we don't really want to do that. So I'm going to get my little coordinate plane here set up so that now we can try to figure out what the tangent lines at the pole are. And again, if you refer to above, that just requires that you set your polar equation equal to 0. So we're going to have cosine 3 theta equals 0. So this is just a review of stuff we've seen in this class, but it's been a while, and of course from pre-cal concerning solving trig functions. If you remember the technique for doing this, what you really need to do is pretend like I'm kind of erasing right here. We need to pretend that that 3 theta is not there, and we're trying to figure out what angles, when you take the cosine of them, give you 0. And what we're going to do is list out about 4 of those just to make sure we can account for all the angles that might be present. Again, we only want all the angles from 0 to pi. So that's the idea. We're trying to figure out what angles, when you take the cosine of them, give you 0. I'm going to go ahead and animate this next step because realistically what we're really thinking of is doing the arc cosine of both sides. But if you're doing this without a calculator, of course doing arc cosine of 0 isn't much help. So that's why before I kind of erased 3 theta and asked the question, what angles, when you take the cosine of them, give you 0? If you list those off, that'll be pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and they keep going, but 4 is usually enough to get all the answers that we're looking for. Again, that's not equal to theta, that's equal to 3 theta. So because of that, we need to divide all of those by 3, so we end up with the angles pi over 6, pi over 2, 5 pi over 6, and 7 pi over 6. So which of these angles matter? Well, something I don't always recommend because you should be very familiar with the unit circle by now. You should know exactly where these angles are, but I can appreciate sometimes it can get confusing, but make sure you're very comfortable with the radian version of these. I'm going to change those to degrees just to help us out a little bit. We want all the angles from 0 to pi. So because of that, of course, 7 pi over 6 is past pi, or it's 210 degrees if that helps. So those 3 angles are the angles of the tangent lines at the pole. So I'm going to go ahead and draw those tangent lines in then. Theta being pi over 6 would be about there. Theta being pi over 2 is of course our y-axis, and theta being 5 pi over 6 would be right there. So to graph this rose curve, we know the first petal is centered on our positive x-axis. And again, like I was saying in 10.3, you being very familiar with how much of a graph is graphed depending on what the angle is going to be very important. Just to kind of help out here, you can write this in the margin if you want. I'm going to just list off a few of the points here. If theta is equal to 0, we'll be taking cosine of 0, which is 1. So that's why we start off at this point 1 right here. If I chose my next angle to be pi over 6 and plug it in, that would be 3 times pi over 6, or pi over 2. The cosine of pi over 2 is 0, so the next point we would plot is this one, and you can see that's why we're getting this first part of the petal. The next point I can graph, or the next theta I suppose I can pick, would be pi over 3. If I plug in pi over 3 into my function, I'll get cosine of 3 times pi over 3, or just cosine of pi, which is equal to -1, which is why we're being put somewhere out over here where I'm putting a dot. Ultimately, again, I'm just doing these first 3 points so you can see how this graph gets traced out. But again, using your TI-89 to practice this, or making a table of values like you saw me do a second ago, can be really helpful. Ultimately, what we're really trying to do here is illustrate how this rose curve follows the tangent lines that you see here. And you can see once we complete this graph, our petals are in between our tangent lines. And that's what's going to help us define certain areas that we're trying to find. The next part of this, to illustrate using our slope formula from above, is we also want to find the slope of the tangent line at theta equals pi over 6. Because of that, we're not looking for tangent lines at the pole, we're looking for the slope of a tangent line at theta pi over 6. So because of that, we're just going to use this really big formula here, and it's really just a matter of plugging in. The only thing we need to do here in terms of extra work so we can plug in is to find r prime. The derivative of r, which is cosine 3 theta, would be an application of the chain rule. The derivative of cosine 3 theta is sine 3 theta, but since we don't have a plane theta on the inside, we need to multiply by the derivative of 3 theta, which is of course positive 3. But because of that negative sign, it becomes -3 sine 3 theta. So we're going to end up with a big mess here, and I'm going to take all of it and plug it in. R, which is our original function, and that's cosine 3 theta, I'm going to plug in times cosine theta. We're going to take that r prime, plug it in, times sine theta. In the bottom, we'll plug in our r, but in front of that there's a negative, so negative cosine 3 theta sine theta. And then again, we need to plug in our r prime times cosine theta. So there's a little bit we can do here to clean up this slope machine. And again, remember, this is our slope machine. If we plug in a theta, that will give us the slope of a tangent line at that angle. So what we can do here is plug in our pi over 6. We're trying to find the slope of our tangent line at theta equals pi over 6. So we can go ahead and plug that in. And then of course that turns into a big mess that you can see here. So of course just being very careful and simplifying this will be important. You'll notice that the 3 times pi over 6 would be pi over 2. Cosine of pi over 2 is 0, which wipes out all of that other stuff here. All of this goes away. If we plug in the pi over 6 and then multiply by 3, we'll get pi over 2 again, but when we take the sine of pi over 2, that all becomes 1. So realistically, what we're left with is this -3 times sine of pi over 6 in the top, and in the bottom we're left with -3 times cosine of pi over 6 in the bottom. After that, you can maybe appreciate we're going to apply a little trig property here, where we can say that sine over cosine is tangent. Of course, the -3's will cancel, and the tangent of pi over 6 is the square root of 3 over 3. And again, that value we just found is the slope of the tangent line at the angle pi over 6. Okay, the thing that we really need to focus on for the rest of this lesson is not slope. The vast majority of what you're going to see concerning this topic on the AP test will be involved with the topic of area inside these polar regions. So just as a quick little recap and review of how we found area under curves in our regular XY plane, we can take that one step further and apply that to these polar functions. So a little review of that idea. If we wanted to find the area under this function from a to b, but above the x-axis, what we would have to do is, or what we first learned how to do, was to approximate that using rectangles. Eventually, though, we quickly saw that we wanted to add up an infinite amount of rectangles so that we could find the exact area under the curve. What that really entailed was us attaching this idea of integration to a summation of an infinite amount of things. And of course, in this case, we're adding up an infinite amount of areas of rectangles. So to find the area of these rectangles, we would just do base times height. But I kind of switch up the order of that for the sake of these integrals. So again, to break down this formula here that we saw way back in chapter 4, this integral from a to b is telling us to sum up an infinite amount of areas of rectangles from a to b. F of x times dx is the area of one of those rectangles. The height of the rectangle is f of x. The base of the rectangle is a little change of x if there's an infinite amount of them. So that was the idea behind finding the exact area under a curve using rectangles, and the idea, of course, of integration. So how would we apply that now to these polar functions? Well, the same analogy is going to kind of hold true. We're going to split up our shape into simpler shapes and then add up an infinite amount of those areas. So here I just have this random scribble of a graph, and that graph is some function r, and it's in terms of theta. So it's just a regular polar function graph. I want to find the area from one angle to another angle, so be careful. Back in our xy plane, we're finding an area from one x to another x value. Here in these polar graphs, we're going to be finding an area from one angle to another angle, which I'm going to call A and B. So it's that area in red that you see there. So what we need to do is we need to split this shape up, not into rectangles, but into shapes that'll help us get to the exact area. And the shapes that we're going to break it into are wedges, or what I'm going to call wedges. If I split this into wedges, and you can see that there's 4 here, I of course could maybe find the area of each of those wedges, add them up, and then that would give us an approximation for that area. Of course, we don't need to do an approximation here because we're armed with this idea of integration. If we can find the area of one of these wedges, then all we need to do is integrate, because that would be adding up an infinite amount of those areas, which will of course give us the exact area. So think of these pie slices or wedges as the analogy to the rectangles for our polar coordinates. So let's take a look at one of these wedges, because if we can find the area of one of these wedges, again, we're just going to add those up to infinity, or in other words, use integration. Okay, so here's one of our little wedges here. Of course, the length in green that you see here is the length of r, our function from the pole out to a point on the polar graph. We have some angle theta in between those two r's, of course. And then the part in purple is the arc length. Any length along a curve, of course, is called arc length. And what you're going to have to recall from pre-cal if you happen to recall it, is how to find arc length. If theta is in radians, and of course all we deal with is radians, we would just take the r times the theta. So how would we find the area of this pie slice, or this wedge? Well, what we need to realize is as we go out to infinity, this angle right here is getting very, very small. Very, very small. It's approaching 0. So I can't draw that. That would be very hard to draw because basically I'd be drawing a straight line. So to kind of exaggerate that, this is of course not to scale, that's why I'm putting this approximately equal to. As this angle gets smaller and smaller and smaller, what's going to happen is the height of this triangle that you see here is going to be indistinguishable from the lengths of the sides. And again, it's kind of hard to visualize, but again, appreciate that this wedge is so tiny. The angle in between the two sides here, R and R, is so tiny that the height of this triangle that we're seeing is pretty much the same as those two R's on the sides. And because of that, our arc length is now looking more like a straight line. This is such a tiny piece here that that arc length is looking like a tiny straight line. And you can see we're just forming a triangle here, where the base is r times theta and the height is r. So as this wedge becomes very tiny, its area is just given by the area of a triangle, 1/2 base times height. The base is r times theta, the height is r, so we're left with 1/2 r squared theta. But again, remember this theta is shrinking ever so tiny, like up here above, where our base was shrinking ever so tiny for our rectangle. So that's not really a theta, that's a d theta. It's a tiny change in theta. So here we go. Here we have our equation for finding the area of a polar function. All it's going to require you do is take your function r and square it, and then integrate that with respect to theta. So the good news is it's a very basic formula, but seeing where it comes from in terms of it being really a triangle that we're finding the area of can be helpful. But again, bottom line, like most of the things in this course, as long as you know this formula here, even though it can be helpful to know where it came from, is really the most important thing. Okay, so now let's apply this new polar area formula. I'm going to take a look at the example I did in the first slide, where we took our rose curve of cosine 3 theta and graphed it. But now I want to find the area of a petal of this rose curve centered at theta equals 0. In other words, I want to find the area of this particular petal of this rose curve. So we're going to start off with our area formula, 1/2 integral from a to b of r squared d theta. Now I guess here's the good news about using this formula. Assuming you're given your function, and I'm not sure why you wouldn't be, all you need to do is square that function. So a lot of the times, and again, this is why 10.3 was so important, most of the times when you're doing these problems, really it's going to come down to, do you know what the two angles are? I would be willing to bet that for most of these problems, if they're going to give you issues, it's going to be mostly concerning the bounds on your integral. From what angle to what angle do you try to integrate to find the area of what you're trying to find? And again, what you practiced in 10.3 should help you out a lot in terms of that. But in this particular case, what really is going to help us is what we discovered in that first slide. These tangent lines that I'm graphing again, we saw this in the first slide, are telling us where each of these petals is in terms of the angles. And you can see this question wants us to find the area of a petal that's centered at theta equals 0. So again, it's this petal right here. So we need to apply the bounds for the petal here in terms of where it's between, in terms of what tangent lines it's sitting between. So we need to really think about what angle is this right here, because if we can determine what that angle is, we're just going to integrate from that angle to that angle, because that's where that petal lives, and that's of course the petal we're trying to find the area of. So of course it's kind of connected to this 5 pi over 6, but that's not what we want to use. That's this part of that tangent line. We're trying to find this part of that tangent line. So what you need to recall is that's just the negative version of pi over 6. If we go clockwise, that's just the negative angle in terms of pi over 6. So because of that, we're going to integrate from negative pi over 6 to pi over 6. The one petal we're trying to find the area of lives in between those two tangent lines, so those are going to be our bounds. So you can see this is a little more difficult than finding area in our xy plane because it was always very obvious from where to where in terms of x the area was. Here it comes down to finding these angles that the area is between. And then of course once you have that, you can set up your formula. After that, it's going to require that we apply something we saw back in chapter 8. As an additional way to maybe view this, and there are many ways of setting up these integrals, by the way, that can either be the good news or bad news concerning this topic, is there's not just one way to do it. We could have kind of disregarded this negative pi over 6 and maybe just focused on the top half of the petal we were looking for the area of. If you had decided to do it that way, we would be integrating from 0 to pi over 6, but then of course, since that's only taking into account half of the petal, we would have to multiply everything by 2. And maybe this would have been, in a sense, a better way to do it, because of course the 2 and the half would cancel out. But ultimately, again, there are many ways of setting up these problems. Again, that's probably either good news or bad news, depending on the way you look at it. So to make this integral happen, just as a quick review, or if you want to go back and look at this from chapter 8, 8.3, we need to use the power reducing or half angle formulas to make this integral work out. So what we can do is apply that power reducing or half angle formula. I'm not going to go over these steps in necessary detail again since we did this back in 8.3, but ultimately what's going to happen is once you simplify everything, we'll just be integrating 1 plus cosine 6 theta. And again, at this point in our integrating skills, if you don't need to show the little U box to do this, that'll be okay. But just remember, it's not going to be 6 sine 6 theta. It'll be 1/6 sine 6 theta. So make sure you're okay with all those integration skills still. Here, the 1, when you integrate it, doesn't become x. It becomes theta since we're integrating with respect to theta. Ultimately, what's going to happen is we'll plug in the top bound, we'll plug in the bottom bound, and when we simplify all that, we'll end up with pi over 3. If I kind of skip too many steps for you here, you might want to try this in the margin of your notes just to make sure you can get down to this value. But for the sake of space and time here, I'm kind of just quickly skipping over these details. Ultimately, what you're going to discover is that the area in purple here of this rose petal is pi over 12. So, a very interesting process here. The key I need to point out here before I talk about one more thing is these bounds needed to be very specific. They wanted us to set up the integral so that we could find the area of this rose curve, or this rose petal for the rose curve. So of course that had to be set up very specifically. We couldn't set up the one for this one, even though it would be the same area. We couldn't set up the one for this one, even though that would also be the same area. They wanted us to find that very specific one here in purple. So those bounds needed to be very specific. But fundamentally speaking, we could have approached this a different way. What if we wanted to find the area of the entire rose curve? Well, all that would require is that we adjust the bounds. And just again, keep in mind that this rose curve, since it's an odd number of petals, is generated as theta goes from 0 to pi. So all we would have to do is adjust our bounds from 0 to pi, and if we went through that whole process of integration again, we would find the area of the entire rose curve to be pi over 4. And that makes sense. The area of this rose curve is pi over 12 from what we discovered before. Of course, all of them have the same area as pi over 12. So theoretically, we could have just taken those pi over 12s and multiplied by 3, which would have given us the same value that we just found when we set up the integral to go from 0 to pi, which takes into account all the petals. So hopefully it's not too overwhelming to kind of see this in a bunch of different ways, but there are different ways to finding the areas of these polar functions. Okay, now we're going to really take a look at some of the more challenging ones. Not that the rose curves aren't challenging, but I think once you start looking at some of the cardioids or the limacons, that's where things can get a little more complicated. What we're going to do on a lot of these is only focus on the setup. A lot of the times on the AP test, it'll be only about the setup and you don't have to worry about finding the actual area. or it'll be a calculator problem, and of course you can just use your calculator to actually find the area. So what we're going to focus on in a lot of these examples is just the setup, as that is of course the most important thing. So here we have our graph of 4 plus 8 sine theta. We want to find, or we want to set up the integral needed to find the area of our inner loop. So what we need to do is to find the tangent lines at the pole. But I think before we do that, it's going to be very helpful, again, like you heard me saying in 10.3, and I'm going to do it for this example, to figure out how this graph is traced out if you were to plot the points. So if you want to make this little table on the side, just so it doesn't take up the space for the notes here, you can. I'm going to pick some thetas and figure out what the r is that corresponds to that. So the first angle I'm going to pick is, of course, 0. If I plug in 0 to my function, I'll end up with a 4, so you can see our graph is starting right here at 4. If I were to plug in pi over 2 into our function, I'd end up with a value of 12. So you can see, it looks like our graph is being traced out in this direction here. So that would be the next point I'd have to plot, is up here at 12. If I pick another angle, say pi, and plug that into our function, we'll end up with 4 as a value. So if we go over to our angle pi, which is over here, and we go out 4 units, I know it says -4, but these are our x and y values. If we go out 4 units from the pole, that'll put us at that point, so you can see that our graph is now being traced out following that direction. I'm going to plot one more point. Again, this is just to give you an idea of the angles used to graph pieces of this particular polar function. The last angle I'm going to pick to illustrate what's going on here is at 3 pi over 2. If you plug in 3 pi over 2, you'll end up with 8 times sine of 3 pi over 2, which is -1. So that'll be -8 plus 4, which is -4. And then at our angle of 3 pi over 2 here, we need to go in the opposite direction 4 units, so that'll put us right here at 4, of course. So after we get to that value, we're going to come around, and then now you'll start seeing the inner loop being formed. Of course, if you go around all the way to 2 pi, we'll get back to where we started. So again, seeing the way this graph is traced out is going to help us immensely, so that we can figure out what angles we need to integrate from so that we can set up this integral. And of course, we're trying to find the area of this inner loop right here. So we need to figure out, where does it start, which is where I'm circling, and where does it end when it gets back there? What are those 2 angles where the loop of the inner loop starts and where the inner loop ends? Because if we can find those, then those will of course be the bounds on our integral. To find those, we need to practice using that idea of finding the tangent lines at the pole, because that's where that inner loop would start, and that's where that inner loop would end. So what we need to do is set our function equal to 0, we'll subtract 4, we'll divide by 8, so we get sine of theta equals -1/2. Again, solving these trig equations should be hopefully very basic by now, but it's all going to come down to your unit circle knowledge. Again, I'm writing that we're doing the arc sine of -1/2, but realistically, without a calculator to set this up, that's not going to be too helpful. So you need to be very good with your unit circle. So if you need to pause and take a look at your unit circle, I would definitely do that. But the values for the angles that when you take the sine of them give you -1/2 are going to be 7 pi over 6 and 11 pi over 6. And again, remember, we want all the angles between 0 and 2 pi, since that's where this particular graph exists from. So I'm going to graph those 2 lines, 7 pi over 6, and I could keep it going on the other side, but I went ahead and didn't do that. It's kind of up to you if you want to keep the line going. But ultimately, that's telling us that our inner loop starts at 7 pi over 6, and it comes back around to the pole at 11 pi over 6. After that, there's nothing else we need to do other than taking our function and squaring it, and then integrating that with respect to theta. So you can see, like I was saying in 10.3, and I think this is a perfect illustration of that idea, your success with these problems really depends on, can you see where a particular polar function starts and ends at. In this particular example, it's kind of a little bit of a different case, but same idea. We want to find the area of the inner loop for 1 plus 2 cosine theta. So we need to find those tangent lines, like the problem above, very straightforward in terms of the algebra. And now it comes down to your unit circle knowledge. Again, I hesitate to even put this here because we're really not doing arc cosine. We're setting up this integral without a calculator, so arc cosining both sides doesn't really help as much as thinking about the unit circle. What angles, when you take their cosine of them, give you a -1/2? Again, I would pause here, look that up on your unit circle. But from 0 to 2 pi, the two angles where cosine is a -1/2 is at 2 pi over 3 and at 4 pi over 3. So again, if I draw those in, I could keep the lines going if it helps you see it a little bit better. But ultimately, what we're discovering is that our inner loop starts at 2 pi over 3 and it comes back around to the pole and it ends at 4 pi over 3. So between those two angles, our inner loop exists. Once you set that up, the rest is really easy. You're just going to take the function and square it, and we're integrating with respect to theta. So in this next example, we're going to take a look at the area bounded by two polar curves. We're not just looking at the area inside one particular polar curve, we're looking at the shared area, or the area bounded by two polar curves. So here's the graph of our two polar curves. 6 cosine theta is our circle that you see in red, and then the 2 plus 2 cosine theta is our cardioid that you see in blue. So we're looking for the area that you see here in yellow, the overlapping part, the area shared by these two graphs. Of course, this piece here and this piece here only applies to the cardioid, and then this moon shape over here only applies to the circle. So we're looking for the shared area. So realistically, just like we would have saw back in chapter 4, let's say, or even chapter 7 when we're looking at two graphs, we need to find the intersection of these two graphs so that we can figure out how to set up some integrals to help us find this area. So luckily, to find the intersection of two polar graphs, it's the same idea like finding the intersection between two regular xy graphs. We're going to set them both equal to each other and solve. So what we can do is take the 2 that I factored out from our 2 plus 2 cosine theta equation and divide that to the other side to get 3 cosine theta equals 1 plus cosine theta. If I take the positive cosine theta and subtract it to the other side, 3 cosine theta minus 1 cosine theta is 2 cosine theta, and that's equal to 1. If we divide both sides by 2, a not too bad equation to solve, pretty straightforward. And now again, like the previous two examples, if you want to pause here, maybe take a look at your unit circle, or possibly, if you haven't memorized, this should be pretty quick to figure out. What angles, when you take the cosine of them, give you 1/2? And again, I hesitate to put this here because we're doing this without a calculator, but really we're thinking about doing the arc cosine of 1/2. The two angles that we're looking at here are pi over 3 and 5 pi over 3. So what I'm going to do, because of symmetry here, is I'm going to only consider the top half of the shared area. Of course, whatever integral I end up setting up, I'm going to just multiply that entire thing times 2. That'll just help us see this integral set up a little bit easier, and of course make things in a sense a little more straightforward in terms of setting up these integrals. So I'm going to set up just the integrals for the top half of this area and then multiply by 2. So we have two areas here. I'm going to label one area as 1, which is going from angle 0 to pi over 3, and then I'm going to label the other area as 2. So what we need to do is set up these two integrals now. And then of course the reason I have this 2 here is because I'm only considering the top half of the area. So to get the total area, I would just have to multiply by 2. Okay, so let's set up the integral for area 1. The integral for area 1 would be the integral from 0 to pi over 3. That area exists from 0 to pi over 3. What function, though, does that area take into account? Well, we're dealing with our cardioid in that case, so that's going to be the 2 plus 2 cosine theta, and all of that, of course, has to be squared by the formula. And then again, don't forget that 1/2 in front. So that's the integral for area 1. To find or to set up the integral for area 2, we need to understand from what angle to what angle that area exists. Of course, it's starting at pi over 3, and then it's ending, and it's kind of harder to see because we're back down here at the pole, but it starts from pi over 3 and ends at pi over 2. Once you see that, we're just going to set up that integral from pi over 3 to pi over 2, and then the polar function that that area is taken into account is, of course, of our circle, 6 cosine theta, and then we'll square that. Aside from that, theoretically, you could just leave it set up as this big mess. I'm going to just clean this up just a little bit and distribute the 2 to both of those halves so that they'll go away. And then we're just left with 2 separate integrals, the integral from 0 to pi over 3 of 2 plus 2 cosine theta all squared, plus the integral from pi over 3 to pi over 2 of the function 6 cosine theta squared d theta. Okay, so hopefully those previous 2 slides are now getting us ready to attempt this AP test free response problem, calculator allowed. We have 2 graphs here. We have the graph of r equals 2, which is just this circle right here that has a radius of 2. And then we also have this kind of like, not quite a limacon, not quite a cardioid. I'm going to just call it a dimpled limacon. But either way, the equation of that is 3 plus 2 cosine theta. We're letting r be the region inside the graph of the circle and also inside the graph of the limacon, as you can see shaded here. And we want to find the area that's shaded, or r. Before we can do this, just like the previous example, we have these 2 overlapping polar functions, so we need to figure out where they intersect, because those 2 angles are going to become very important in terms of the setup of our integrals. So here, once you set those 2 equal to each other, we can subtract 3 to get a -1, divide by 2, and yet again, it's going to come down to your unit circle knowledge. Make sure you either have that all memorized in your head, or at the very minimum, you have that in front of you, so you know how to identify what angles, when you take the cosine of them, give you -1/2. Again, we're really thinking about doing the arc cosine of -1/2, but even though this is a calculator problem, your calculator will only give you that first angle. So you'd still need to have your unit circle memorized so that you could also appreciate that there's another angle, and that's 4 pi over 3. So ultimately what we've discovered is that those 2 intersection points are at those 2 angles, 2 pi over 3 and 4 pi over 3. Okay, so now we need to figure out how we're going to set up these integrals. So what we need to see is that our circle starts at this tangent line of 4 pi over 3 and then goes all the way to our other tangent line of 2 pi over 3. Our limacon starts at 2 pi over 3 and then goes up to 4 pi over 3. So of course, all of those angles are going to play a part once we set up these integrals. And what we need to realize is when we set up the integral for the circle one, we can't start at 4 pi over 3 and then go to 2 pi over 3. That's going backwards in a way. So what we need to realize is that really 4 pi over 3, if you go in reverse clockwise, would be at -2 pi over 3. The reason that's important is because now we need to set up the integral to find the area of the circle. And we're not going to go from 4 pi over 3 to 2 pi over 3. Again, that would kind of be going backwards in a way. We need to go from -2 pi over 3 to +2 pi over 3, kind of like an example you saw previous with the rose curve in a previous slide. Of course, all we need to do after that is take our polar function, which is just the number 2, and square it, and we're integrating that with respect to theta. To set up the integral to find the area of the limacon, that's a lot more straightforward now. All we're going to do is set that integral up to be 2 pi over 3 to 4 pi over 3, and then of course we're going to integrate our r squared, which is 3 plus 2 cosine theta all squared. If everything made sense up until this point, and by the way, don't forget those halves, a very easy thing to forget in this formula. Assuming all that goes okay and you're okay with that understanding, I would definitely pause here and see if you can get the integral of this, or the value of that, and then also for this one. If that all went well in your calculator and you did that, you should find the value for your first integral times a half would be 8 pi over 3, and the value for the second integral, and unfortunately it's not an exact answer here, so I'm going to leave a bunch of decimals, you should find that to be 1.99289. Ultimately, we're looking for the area of the R, or the shaded region, so if we take those two and add them together, we'll get 10.370. Again, remembering to leave 3 decimal places for the AP test. Okay, here we have another AP free response question, and in this case, no calculator. So we have the graph of a polar function here, 1 minus 2 cosine theta. It's one of our spiral graphs, and it's being graphed from only 0 to pi. S is the shaded region here in the third quadrant, bounded by the curve and the x-axis. I want to write an integral that'll help us find the area of S. We're not going to find that area, we're just going to write the integral. So, kind of like we've been practicing since 10.3, we need to understand how this graph is traced out. Does it start over here and go this way? Or does it start here and go in the opposite direction? Once we kind of figure that out, then we'll understand where the shaded region lives. Between what two angles does that shaded region live between? So what we can do first is plug in 0 into our equation and see where this graph starts. R of 0 would be 1 minus 2 times cosine 0, which is 1, or negative 1. So as it turns out, the start of this graph is right there when theta is equal to 0. So then how do we figure out where it ends at? Right here. Well, what we need to realize is that at the pole, R is equal to 0. And if R is equal to 0, which is our end to this little area, then we just need to set our equation equal to 0 and solve. And you've seen a lot of these already in this lesson, so hopefully this is nice and simple. Cosine of theta is equal to 1/2 when theta is equal to pi over 3. So the start of this shaded area is at 0, and the end of the shaded area is at pi over 3. And that's all we need to do. Once we realize that those are the two bounds we're dealing with, we'll put those on our integral, and then of course we'll take our r and square it, and then just don't forget that 1/2 in front of the integral. And that's all we needed to do. Of course, we could find that area, but without a calculator, that would take some time, so we don't need to do that. In part B, we're going to go back to a question we've seen many times in this course, although it's been a while. We need to rate the equation in terms of x and y for a tangent line equation. And that tangent line is going to be at the point where theta is equal to pi over 2. So luckily we can at least start with what we should always start with when we're dealing with these tangent line equations, our tangent line formula. After that, it's a matter of figuring out what our slope is, what our y value is, and what our x value is, and of course we can plug those in. So let's go after the x and the y first. If you recall from 10.3, to find x when you're dealing with polar equations and to find y when you're dealing with polar equations, we can use these two formulas right here. X is equal to r cosine theta and y is equal to sine theta. So of course we know what r is in this case. It's our function, 1 minus 2 cosine theta. If we take that and evaluate both of those at pi over 2, and because of space running out here, I didn't show that, but if we take pi over 2 and plug it into this equation, and plug it into this equation, we'll get a point. That point, if you want to practice this again on the side to make sure, to verify these numbers, you can get them. You'll find an x value to be 0 and a y value to be 1. Next, what we can do is find the slope. And we only practiced this one time previously in this lesson, so it's a good thing to practice it again. To find slope, dy dx, we have to use this very complicated mess of a formula. The bottom line is, we just need to plug in some stuff. The very first thing we need to do, because it's really the only thing that's left to address, is to find r prime. The derivative of r, which is 1 minus 2 cosine theta, would just be 2 sine theta. Once we realize that, we can take the r and the r prime and plug it in appropriately into the equation. We want to find the slope of our tangent line so that we can write the equation at pi over 2 for theta. So what we need to do is plug in pi over 2. We can actually simplify this a little bit, and it's not necessary, but it will clean things up a bit. We can distribute the cosine theta, we can distribute the sine theta in the bottom, and once you clean up a lot of stuff, you'll end up with this expression. But bottom line is, we really didn't have to do that. It just might help us a little bit in terms of evaluating this big fraction at pi over 2. So if you plug in pi over 2 into this fraction, very carefully, you'll get cosine of pi over 2, which is 0, cosine of another pi over 2, which is 0, but we're squaring it, sine of pi over 2 is 1, and then the bottom kind of works out with those same values. Ultimately, if you're very careful with this entire process, you'll find that the slope of your tangent line, when theta is equal to pi over 2, is equal to -2. Once we get that, it's just a matter of plugging in all our values. We know that x is 0, y is 1, and we just discovered that our slope is -2. You don't have to clean that up. If you remember, on these free response questions, it's best just to leave it unsimplified, or you can actually simplify it if you trust that process. Okay, one more type of area problem that you might run into will be the area bounded by two polar curves. So just as a quick recap, the first type of area we found with these polar functions was the area inside of a polar function. First we did a rose curve, then we did the inner loop of some limosans. The next thing we did was the area shared by two overlapping polar functions, which required different techniques depending on how they were overlapping. The last type of problem involves us finding the area between two polar curves, not the area that they share, but the area that's between them. If we were trying to find the area that they share, I guess that would be this area right here that I'm shading in. But that's not what we're trying to find. We're trying to find the area between the two polar curves. And here I'm calling that area A and shading it in red. And we're finding that area from theta equals A to theta equals B. So to find that area, we're just going to rely on simple geometry. If we found the entire area here for our f function, and we found the entire area here for our g function, we would just take those two values and subtract them to get the area for A. So that's what we're going to do. We're going to find the area for the f function, we're going to find the area for the g function, and subtract those two. So the area bounded by two polar curves, if they happen to be called f and g, would be f of theta squared minus g of theta squared. And we're integrating with respect to theta. So we kind of saw this back in chapter 7, where we dealt with maybe a top minus a bottom or a right minus a left, and it was a lot easier to maybe remember it using those words instead of f and g, because your functions aren't always going to be called f and g. So because of that, a more intuitive way to maybe remember this is to kind of think about their position relative to the pole. I'm going to call f the far function because it's furthest away from the pole. I'm going to call the g function the near one because it's closest to the pole. So a more intuitive way to maybe think of this formula will be, of course, 1/2 integral from a to b. But instead of f's and g's, it's maybe easier to remember it as the far function squared minus the near function squared d theta. So to illustrate this idea, here we're going to find the area bounded by the function r equals 2, which is this circle right here, and r equals 1 plus 2 cosine theta, which is the limasan. We want to find the area of the crescent-shaped region between the two curves, and that's the key, between the two curves. We don't want to find the overlapping region. We want to find the area between these two curves. So because of that, we need to set up this integral. The intuitive way, again, is to remember it as far squared minus near squared, but I'm going to be specific in terms of this problem. The far function, the one furthest away from the pole, is our limasan. The one closest to the pole is the circle. So I'm going to even rewrite that equation with the specifics of this problem. It's going to be the limasan equation squared minus the circle equation squared. And of course, that's really easy to do. You're just going to plug those two equations in. So like with every one of these problems in this lesson, it's all about the bounds. So how are we going to find those bounds? Well, when we have two graphs intersecting, we need to find those intersection points. Or I guess with regard to this topic, really those intersection angles. To do that, we're going to set the two functions equal to each other. And like you've seen many times with these examples, it's pretty straightforward. Subtract 1, divide by 2, and now again we need to ask ourselves the question, what angles, when you take the cosine of them, give you 1/2? If you're up to speed with with your unit circle, you'll find that it's pi over 3, 5 pi over 3. If you happen to use your calculator in a sense to cheat to find that, remember your calculator will only give you that first value, so you still need to be good with the unit circle to find the other value. So it's best to just always look at it from the point of view of the unit circle. Once we discover that, we're kind of ready to set up our integral. But what we need to keep in mind is that this intersection, which was 5 pi over 3, and this intersection, which was pi over 3, are our bounds. But we can't integrate from pi over 3 to 5 pi over 3. That would be that area that I drew off right there. If we integrated from 5 pi over 3 to pi over 3, we'd end up going in a totally wrong direction in a sense, because we're going backwards. 5 pi over 3 to pi over 3 would be taking us in a backwards direction. We're looking for, there's a lot of lines here, we're looking for this right here in blue. So how do we integrate? Well, what we can realize is that at this angle, even though it's 5 pi over 3, we want to start from the negative version of that angle. The negative version of that angle is negative pi over 3. And we want to integrate from there to our positive version of pi over 3. So just keep that in mind. We can't just always take these bounds blindly. We need to sometimes think about, like you've seen in several examples, whether or not we can actually use that bound as you see it. And here, we can't use 5 pi over 3. We want to integrate from negative pi over 3 to pi over 3. Ultimately, once you kind of sort out all that concerning the bounds, this is a calculator problem, and again, I would urge you to pause here and attempt to type this in your calculator, but if everything goes okay, you should find the area in green to be 3.283.